All right, hello, and welcome to our final lesson about finite automata for at least this little while. In this video, we are going to talk about the relationship between deterministic and non-deterministic finite automata. So first of all, if we propose something like every language that can be generated by a deterministic finite automaton can be produced by a non-deterministic finite automaton, this should be an obvious conclusion to you if you really understand the definitions of the two things involved, because every deterministic finite automaton fits in under the definition of a non-deterministic finite automaton. But vice versa, this is not necessarily as obvious that this would be the case the other direction. So in this direction, if you can deal with a language with a deterministic finite automaton, it makes sense that you should be able to deal with it with a non-deterministic one, since it already really is a non-deterministic one. What is less obvious is that the opposite is actually true. That every language that can be generated by a non-deterministic finite automaton can also be produced by a deterministic finite automaton. And this is tricky to do, and the explanation in the book is a little confusing, so we're going to go through exactly how it is that we can conclude that this is the case. So let's start off with an example of a non-deterministic finite automaton. So this is the automaton that we have in the book. We can tell that it's non-deterministic because out of this state Q0, we have two different options for where we can go if we read in a B. And so there's this can't be deterministic. It has to be a non-deterministic automaton. So the function that determines where these arrows go, etc., is delta for this non-deterministic automaton. And what this tells us is that if we're at state Q and we want to add a B, we can go to either of the two in the set, right? We can either go to state Q0 or to state Q1, right? Either option in the set. Whereas if we're in state Q1, we only have one option for where to go for each of those, which is Q0. So what makes this most essentially non-deterministic is that we have sets here instead of individuals members, right? So these on this side, if we wanted it to be deterministic, we'd have to have these be states, right? These would have to be states, not sets of states, right? And that's the essential difference between that's the most essential difference between a non-deterministic and a deterministic automaton. But one thing that we can do if we want to turn this into a deterministic automaton, this almost looks like a deterministic automaton, right? The left side is all set up to be deterministic. The right side has a thing on each side. All that we have to do is stop thinking of these as sets of states and just think of them as states, right? So this is the state in which you are in both states, right? This is the state in which you are just in state Q0. This is the state in which you are just in state Q0, right? So to express what we're doing here, we're going to rename this set. Anywhere where we see this set appearing, this is going to be called this in square brackets, right? Anywhere where we see this set appearing, it's this in square brackets. Anywhere we see this appearing, it's this in square brackets. And anywhere where we see an empty set, it's this in square brackets, right? So these are now going to be the four states of our deterministic finite automaton. Now it's a little more complicated than just making three relations between three different things, as we'll see once we start working this out. So we've put our four states here, and now the first step we have to do is we have to determine which is our start state. So if we go back to our original, we had it specified that Q0 was our start state. This is hard to see because I didn't draw the line very thick. But Q0 was specified as our start state, which means that whatever is labeled as just Q0, right? So this state is our only Q0 state, is going to be our start state. So this is our start state. That's the only place we can start in our new deterministic finite automaton. Now we have to look at our final states, right? So our final states, anyone where you end up in Q1 qualifies as a final state. Now this is a little bit confusing. So the first one that's obvious is if you end up in Q1, that should be a final state, right? The state where you're just in Q1, that should be fine. But interestingly enough, this is also a final state, right? Because being in the state where you're in Q0 and Q1 means that you must be able to be in a final state as well, right? So because you've got Q1 here as part of your label, this is also going to be a final state. Which means that our only non-special state is going to be this one, right? You are not in a final state at all if you're just in the empty set, right? All right, so how are we going to do this? So the first step is we look at when we start in Q0 in our original automaton, what can happen to you if you're in Q0? You can either go into Q0 or into Q1. So what does that mean? You're going into both, and our label for being in the state of both being in Q0 and Q1 is this, which means we have to draw an arrow here, and we have to label it B, right? If we start out and we add a B, we end up in this state. What happens if we start out and we add an A? We end up being in the state of not being in an automaton in any of our states, right? So we're in a state of not being in any, which is the same as being in the state of being in the empty set, right? So if we add an A, from there we go to here, right? If we add an A, that's what happens. Here, let's put our other form of the A, just so it's easier to read. A. Now let's look at what happens if you're only in Q1, you're just sitting in here, and you add an A, right? We just have one option, and that option is to go to Q0, right? And so this option is our A. Now what's happening if we're only in Q1 and we add a B? That takes us again only to one other state, which is Q0. So we add another arrow here, which is going to take us to Q0 if we add a B. All right, so those have been the really easy ones that you can get just by looking at this chart without doing any sort of extraordinary thinking. But we aren't done yet, because we haven't talked about what happens when we're in this state or in this state. All right, so if we're in the state of being not in a state, this is kind of weird, but if we are sitting in this thing and we're not in either of these states, what happens when we add an A? Right? If we add an A and we're not in this system at all, you're not gonna end up in the system magically, right? So you end up either an A or a B. If you're not in the system, you can't enter the system just by teleportation, right? There's no way to just enter this system from the outside, right? So if you're not in a state already, you're going to stay being not in a state, whether you're adding an A or a B. So that's where we get these arrows from. Now we have to talk about this state. How do we get in and out of this state? So if we are in the state of being in both Q0 and Q1, so imagine you could exist at the same time being in both Q0 and Q1. What happens to you when you add a B, right? So if we go from Q0, we can get to Q1, or we can get to Q0, or we can get to Q0, right? So there's a bunch of different ways we can add B's if we're in either of these, right? So if we're in Q1, we add a B and we get to Q0. If we're in Q0, we add a B and we get to Q0. If we're in Q0 and we add a B, we can get to Q1. So we can get to if we add a B, regardless of which state we're in, we just know we're in one of those states. We know that we're going to be in one or the other of those states. So that means that B takes you back into the same state you were in before. But what happens if we are in one of these two states and we add an A, right? There's nowhere we can go from Q0 to get into another state by adding an A, but there is some place we can go from Q1 to get into another state by adding an A. But we know that regardless of which one of these we're in, if we're in both, right, if we know that we are in both, the only one you can get to from here is Q0. And so that means that even though we're in a state where we're in both states, by the time we add an A, we know that we're back here. So this is now a deterministic finite automaton, and we can write out the function for this. So the function for this is going to look like this, right? It's going to be a bunch of pairs. So if we are in the state of only being in Q0, and we want to add an A, we end up being in the state of being in the empty set, right? If we are in the state of only being in Q0, and we add a B, then we end up being in the state of being in Q0 and Q1. If we are in both Q0 and Q1, and we want to add a B, we end up being in the state of being in both Q0 and Q1. And so on and so forth. I'm not going to write it all out, but you can understand how this function is going to end up looking. And this allows you to take any non-deterministic finite automaton and turn it into a deterministic one. So this is a little bit confusing, and I encourage you, if the example in the book, which is just this example, and me walking you through this example is not enough, there are other places where you can see this proven on the internet. I encourage you to check out other places, because this is a really good, this is not really all that crucial to, your future life to know that this is a fact, but it will certainly ensure that you understand both deterministic and non-deterministic finite automata and how they work. And if you can understand this, then you get them. So I encourage you to check out other stuff.